first answer is, well, using the blue box technology is not needed to select anything, because it's totally, the noise suppression is totally automatic. But it's important to clarify how you can do in order to remove the noise. How is possible using other technologies. For this aspect, I would like to explain my screen here. Well, the way to remove the noise is sorry, because my computer has independent life. Yes, now, how to remove the noise? The way to remove the noise using other technologies is looking for the spectrum, frequency in the spectrum of the noise. For the reason, the way is to measure with the background noise. This is important difficulty, because background noise involves that in this moment you have to measure only the noise, not the PD signals. How to do it? Is not easy in on-site, because the best way is to remove the high voltage in order to have only noise, but it's not easy, it's not realistic. How to do it? Well, the way, probably the best way, is to place the sensor very close to the real position. The real position of, for instance, of high frequency sensor is to clamping the conductor that connect the termination with the earth. Well, the way to measure the noise is to remove this high frequency sensor and to place the sensor close to this conductor, in order to acquire signals in the environment, but not exactly the signal through the conductor. That is probably the PD signals. It's an approximation to measure the noise. The best way to measure the noise is to decentralize the installation and to measure only the environment noise, but this is impossible. But in any case, in a laboratory, of course, it's possible, because we can measure without voltage, high voltage, and we have this signal in the time domain. If you obtain the frequency, in the frequency domain, the signal, you can obtain this spectrum. And in this spectrum, you can see in what places you have less energy of the noise. But if this condition is only satisfied if you have only the noise signal. In the reality, it's not easy. It's not easy to do it. For the reason, other technologies that have to look for what is the noise level, the best way is to place the sensor close to the realistic or the real position when you place in the conductor, but it's an approximation. And of course, the question is also related with what is the best bandwidth to measure. Of course, to measure partial discharge with, for instance, with this kind of noise will be the minimum energy. What is the frequency? What is the frequency where the energy is, noise energy is the lowest? But in this case, is 1.2 megahertz. This will be the central frequency, measuring frequency. I will choose this frequency. And in what bandwidth? The range, well, the bandwidth plus minus 0.5 megahertz is a typical range that you can measure in order to acquire the information. But the difficulty in practice is to know exactly what is the spectrum of the noise. This is the most difficulty. But using the blue box technology, this is removed. This is no problem, because the blue box technology use Wellet transformer. The Wellet transformer is carry out these ideas automatically is looking for different frequencies in all frequency bands in order to acquire the best relationship between signal and noises, and to recompose the real signal with the best solution. Of course, when you use filtering, when you use the Wellet transform, also you are attenuating the signal. You are removing the noise, but attenuating the signal. It's clear. You have to pay a contribution to remove the noise, but the signal you can distinguish pulses from noises, from exactly the noise that is modulated noise. The Wellet transform remove very well the modulated noises. The Wellet transform plus statistic, the blue box technology, only discriminate pulses, only pulses. Is a methodology in order to identify pulses, only pulses. And what is the meaning? The meaning is if you have broadcast noise, you have modulated noise, is automatically suppressed. But if you have a noise, pulse noise that can appear, electronic pulse, electronic power provoke pulses. In this case, you have another kind of noise that you can the opportunity to remove using clustering techniques. Javier have shown the clustering method within a three-dimensional space where you have different clouds. One of these clouds could be a noise pulse noise, coming, for instance, for electronic power. Wellet transform, blue box technology, removes automatically the modulated noise, but pulses noises maintains, because at the a priori, you don't know if a pulse is a partial discharge pulse or is an electronic pulse due to electronic noise. For reason, the second step is to use the clustering techniques in order to identify the cloud that is only corresponding to the noise. This is two different kind of noises. I think this is the question that you are. I think is I have tried to answer the question. I don't know if you have, but this is about the first question.
Thank you, Professor Garnacho. I think you have covered first question very good, especially regarding how to distinguish with the noise. Saya akan kesulitan merangkum jawaban Profesor Garnacho yang cukup panjang tadi, tapi intinya tentang bagaimana membedakan noise dan lain sebagainya. Saya rangkum di satu pantun singkat mungkin. Tes PD itu berat, kamu nggak akan kuat, pakai blue box teknologi saja biar nggak sakit gigi. Kira-kira jawabannya begitu. Intinya, pertanyaan yang mendasar adalah bagaimana membedakan itu dilakukan oleh blue box teknologi, di mana disitulah blue box teknologi mendapatkan patennya. Salah satu yang sudah dipatenkan adalah memisahkan atau mensupres.
Well, this is a good question because it's important to know how was performed these tests. Because of course, the first question, the first clarification could be to know where was the noise source. It was inside of the GIS. It was in other elements connected to the GIS, in the cable, in transformers. The first question is to know exactly, but assuming that it is in the GIS, well, the next clarification point would be it was an eventual sporadic PD pulse for in the energization process, because it can be occurred that when you connect with the high voltage, in the first instance can appear several charge movements, but only eventual periodic, no maintain it. And in general, if we have experiences, partial discharge in GIS, we have several experiences in small electrodes, floating electrodes can appear. We have experiences in ultra high frequency sensors, invasive, that our experiences provoke small PD sources, PD pulses. But in this case, in the question is difficult to answer in a correct way, because the first is to know if you have identified if the partial discharge source was inside of the GIS. And for the reason, the most important is to identify the PD pattern. If you identify the PD pattern, you can identify probably what is involved. What is involved? Is involved the CFCs, is involved a cavity, is involved a surface in air, is involved a surface in CFCs. And this is, in general, in my opinion, in this test, you had to identify where is and what is involved in this PD source. If you have only a figure about PD amplitude, is not enough. I think, in my opinion, is identify the activity and identify where is this PD source. In this case, you can clarify the problem and identify if the problem is related with the EC-physics. For the reason, this question is difficult to answer if you don't know exactly what is the PD source and how it was produced. But my criterion is, if you have this situation in the next future, is to identify in a better way where is the PD source and what is involved in this PD source. And after this question, you can answer the criticity of the PD source. This is complementary to the last question, because this is very nice, because if you identify a problem, now you have to solve the question about what is the problem and how to do it. I think you have two alternatives. If you have spacers, you can measure by external sensors using TEV sensors. But if you don't have spacers, you have to use acoustic sensors. If you don't have the opportunity to have invasive sensors. Of course, if you have the opportunity of invasive sensor, is the best way to localize the position. But if you don't have, you can use the spacer in order to play TEV sensors, or acoustic. By acoustic phenomenon, you can identify the compartment. And in this case, you have the capability to solve the problem, make the next decision using this kind of sensors. Okay, thank you.
To show you the answers for these questions. This is a table. Sorry, because part of the test is in Spanish. Okay, can you see the screen? This
Yep.
to have the severity of the different PD. The first step is to identify which is the type of PD. Okay, so we need to distinguish where is the PD located. Is affecting to a solid insulation, is affecting to air insulation, to oil insulation, or is affecting to SF6 insulation. And when we know the type of phenomena that is affecting for the type of insulation, then we can establish a criteria based on the experience. Of course, we have a lot of experience for example, solid insulation. We have been detecting since the beginning of PD activity until almost the failure of the insulation. So we know exactly parameters of the monitoring to establish if we are in a critical condition or we are just starting with the defect. So we can establish like a red criteria or something critical or something orange, depending on the levels of the activity. We identify for the level of the activity the magnitude of the PDs, of course. We will be measuring in millivolts if we are measuring in service, or we can measure also in picocoulombs, but this level is very important for some of the phenomena, not for all of the phenomena. And we have to analyze always, because it's very important, the number of pulses per period of the voltage. If we analyze these two parameters, the amplitude of the pulses and the number of pulses per period, we can establish a severity for each phenomena. Okay, but we need this information: the type of insulation affected, type of element, type of phenomena, and the levels. Levels is amplitude and activity, number of pulses. And of course, when we are doing a spot monitoring, we will have just a picture of some minutes. So this is not a lot of information, but if we are doing continuous monitoring, we can collect a lot of information about the performance. If the problem is generating PD 24 hours per day, is the degradation, the evolution of the defect is very fast. If the problem is just generating PDs in some moments, in specific moments of the day, because it's intermittent, then the severity could be much lower. So we need to identify the element affected, phenomena, parameters of activity, amplitude, number of pulses, and if we have the opportunity, the evolution during the time. Of course, in order to do continuous monitoring or spot monitoring, if we want to choose the best moment, the best time to do the acquisition of the PD, we need to focus in what are we looking for. If we are looking for a cavity, a solid insulation defect, it is very interesting to monitor when the load is lower. Usually when we have a lower load in the installation, we will have increase of incipient PD problems. If we have a problem that is developed, we will have PD 24 hours per day, and doesn't matter when we go to measure. But if the problem is incipient, when the load is lower, when the current is lower for a solid insulation, will be better because we will see the problems. Usually when the cable, when the transformer, when anything is cooler, we will have more opportunities to see the PD. Of course, if we are looking for a problem in a transformer, it's also interesting to have when the current is higher, because the overheating can damage the paper, can damage some insulation inside the transformer, and it's interesting to monitor when the current is lower, when the temperature is higher. And also, for a transformer, we can identify problems at the surface when appear the bubbles inside the oil. And this moment is when there is a fast change in the temperature of the insulation. So depending on the insulation, we need to choose the proper moment. For cables, for anything solid, when the current is lower. But for the transformer or anything with oil, it will be more interesting to cover a wide range, to have a full cycle of the load, to know what happened when the load is high and when the temperature is changing. Also, for the GIS insulation, it's very interesting to monitor during the switching. When there is a switching in the substation, there is a transient over voltage that can start the PD activity. This PD activity will be just for a few minutes or seconds. So when we are monitoring in a GIS, when the switching appear and the voltage start the PD, we need to be measuring exactly in this moment, because it's the only moment to detect the PD. Okay, so it depends. Transformers in service, we can do not a good calibration to know exactly the picocoulombs that we are going to measure. So it will be an approximation of the picocoulombs, but the only way to do a calibration is connecting a calibrator through the whole of the sensor, so we know exactly how many picocoulombs are going through the whole of the sensor. And we used to call this more a verification, because we verify that the sensor, the cable, and the instrument are working as the first day of service. So we will verify the measuring chain, but we don't know exactly how many picocoulombs are appearing in the installation, because the PD will travel depending on the configuration of the grid, depending on the switches that are open or closed. So depending on the origin, the PD signal that reaches our sensor will be higher or lower, and we cannot do a calibration that is applicable for all the time. It's not possible. And the only way to monitor is just detecting the PDs and identifying that the system is working properly. What we can do for calibration in service with high frequency current transformers, we can also inject the signals with other sensors. If we don't have access to the sensor to do this calibration, we can inject the signal with the other sensors, and we will cross the signal to the other sensors, because there is a crosstalk. So this is another way to verify our sensors that are installed in the permanent installation. This is very similar to what we can do with ultra high frequency antennas inside the compartment of the GIS. We need to inject a calibration signal with one antenna, and we will measure the signal reaching the other sensors. Okay, this is very similar. And this is what we call a verification, not a calibration. And we have another calibrations, very important for synchronized measurements, that are to identify the first thing, that we are connecting the sensors in the same cable. If we put one sensor in one side and one sensor in the other side, we need to verify that we are not putting the sensor in a different phase, and we have a misunderstanding of the phases. So we will inject signal with the calibrator using the sensor, and we need to identify which of the sensors on the other side gets the maximum signal to verify the phases. We will also calibrate the propagation delay. We need to know, for the automatic localization tool, we need to know how much time it takes for a PD pulse to travel from one sensor to the other. So if we inject with a calibrator the signal, when the signal reaches the other sensor, we know exactly the arrival time difference to travel the path of the cable. So these are the calibrations that we can do in service.